but welcome everybody to the Smart Crete Community of Practice for Asset Management. My name's Gavin Chadbourn. I've recently taken over as the lead for the community of practice, and this is I suppose the first community practice session that I'll be leading. Our talks today, we've got 3 speakers talking about a project that's currently ongoing on the intelligent monitoring of corrosion in a marine environment. We've got Rohith from Fremantle Ports, Tasha Eagle from Farzaneh, and Kod Pojtanabuntoeng. Apologies if I've got that wrong, but fortunately we've got a shortened version, Kod, which I can pronounce. So three very good speakers lined up. The format for today is we'll run through all of the talks first, so for about 10 to 15 minutes each talk. So if you have any questions, please put them into the chat, but we'll open it up to a forum discussion once we've had all of the presentations completed, and that will help us keep to time. I'm a stickler for keeping to time, and I hope to get you out of here by 1:30 Brisbane time. So without further ado, we will start off with Rohith Kallem. Rohith is a chartered professional engineer with 19 years of experience in concrete remediation, project management, asset maintenance within the ports and marine sector. Rohith specialises in managing the life cycle of concrete structures, delivering effective repair strategies, and overseeing complex remediation projects from planning through to execution. He has a proven track record in optimizing maintenance programs, improving asset performance, and ensuring compliance with industry standards. He's got a collaborative, results-driven approach and has established strong relationships with stakeholders across government, industry, and contractors, aligning technical execution with broad operational objectives to ensure successful project delivery. He has a deep technical expertise and strategic project leadership to deliver cost-effective, sustainable solutions and improve structural durability and operational performance. Please welcome Rohith. Over to you, Rohith.
Thanks, Gavin, and welcome all. Good morning if you are in the West Coast, and good afternoon for the East Coast. Just give me a second to share my screen. Can you all see my screen okay?
Yes, I can, Rohith.
Presenter mode is just in, oh, now it is. There you go.
Yeah. Thanks all. Thanks, Gavin, again. So I'll better get into it. I'm going to speak a little bit about Fremantle Ports, some of the assets, and the way we are geographically located and spread out, and get into some of the constructions that happened across the port over a long period of time, and some defect management, how we do currently manage and how they've been managed, and set up a scene for the next couple of speakers in defining the problem, what problem we are trying to achieve, and how we are working collaboratively. So Fremantle Ports. So we are a government trading entity owned by the Western Australian government, and our purpose is to facilitate trade through the port of Fremantle. We have 3 precincts. One is North Quay, Victoria Quay, and this is pretty much located in the city of Fremantle, as you know. So it's called Inner Harbour. So I'll get into the other one, but we are split into 3 precincts: North Quay, Victoria Quay, and Kwinana Port. So that's an aerial view of the harbour in the Inner Harbour. And that's more of an aerial view of both the harbours. So we call it Inner Harbour, and I don't know if you can see my cursor, but that's North Quay. We have 4 common user berths. 7 of them are container berths, and on the North Quay, and on Victoria Quay, we have a variety of berths in terms of common user berths, ro-ro vessels, and this bit here is our passenger terminal, we got berth FNG, where we can berth 2 passenger ships, cruise vessels. And just around here, there is a ferry landing just here that goes to Rottnest Island, which is one of the major tourist attraction in WA. And we do have some berths in the inner harbor that were built around in this area here around before 1927, and they are all heritage listed. So that's most of the berths on inner harbor. We do have some operational berths, but most of these on the western side of the Fremantle are all public precinct areas. So public got a good full access to all the berths around here. And we do, and on the outer harbor, we have Kwinana Bulk Terminal, where one of the jetty is not in operation at the moment, where we do all dry bulk, like cement clinker, silica sand, and other bulk products. Kwinana Bulk Jetty, where we do all the dangerous goods like anhydrous ammonia, petroleum, liquids, bitumen, and so on. Just getting into age profile, sorry. Varying ages of different berths, different assets, right from berth 1, berth A, B around Victoria Quay, built in 1927, all the way to 1980s, 2010 as well. And major modifications happened over time to a lot of berths. This is some of the snapshots from our annual report. Just to show you, we got multiple different trades happening, containerized, non-containerized liquids, and so on. I wouldn't go too much into detail, but because of our topic being on the monitoring. Well, yeah, thought this would be some interesting for audience in terms of 1972 on the left, where berth 8 was originally constructed. And then 1980, we had a different berths constructed. These are all container berths, by the way. Berth 8, berth 4 and 5. And then berth 10 as well, that was built in 2010. As you can see, different construction methods, a lot of reinforcement exposed at that time for longer periods of time due to various constraints. I'll get into that a bit more in the next couple of slides. Interestingly, I could able to find a photo of this defect that was from 1984, and that berth was actually built in 72. So in a 12-year span, you can see the significance of concrete damage that was visible and apparent, and being an operational berth, that was significant, defect. And yeah, as you can see, there was a various mix of materials and corrosion and loss of strength of the beam. So that was interesting, I thought. And then these are some of the typical defects that we come across at the port from across all different berths. And these are some of the defects on the piles, where it is very hard to inspect each and every pile because as we are spread across a whole lot of area. So, but when we do experience or inspect, we do see some of the piles have a significant sectional loss, reinforcement loss, and the integrity of some of them are compromised because of the defects. And these are some of the berths, the one I could say around 2010 that were built in with a different type of piles. As you can see, the steel pile is fully wrapped, got cathodic protection attached to it in operation. However, the concrete was left by its own, and some places have minimum cover, some places have more cover, but varying levels of corrosion that we notice across the port. And just an example, in this photo, you can see this pile muff, we call it, has got all of the cover has lost, the reinforcement is all corroded, whereas on the other side, you still got concrete and the cable to the CP system is still intact. Even here it is intact. But yeah. And the difficulty part is, so sorry, before I get into difficulties, how we normally manage our defects at the port is we do visual inspections, we do send divers for underwater inspections, for piles and sheet piles of steel. We do thickness testing, some delamination survey, and then we do some destructive testing like chloride sampling and taking some cores and getting some analysis done so that we can develop a appropriate repair methodology for that particular defects or different type of defects we can address effectively. And we do call them ACAs, so asset condition assessments, which are in accordance with the WAF structure condition assessment manual WISCAM standards. Once we do the inspections, then we, because so many berths, so many defects, we need to prioritize our defects. So we use our Fremantle Ports corporate risk assessment criteria, where apologies for the noise, where there are 6 consequence criteria that are listed on the right-hand side, and reputation is one of the big things for the port as well, being heritage listed area. Some of the structures are heritage listed. And with ongoing operations, there is a lot of on the line in terms of reputation. So we do prioritize our defects before we get into a project stage. And when we get prioritize that and get to a stage where we wanted to do some repairs, we have multiple challenges in terms of berthing availability, shipping schedules change on a daily basis, ships coming in, going out. So we got to accommodate that because that takes precedence. Restrictions to the areas where we wanted to access, not a lot of room between the underside of the deck and the water. Then we do have, considering all the defects, we do put some load restrictions on the above on the deck, so that we are not driving any huge cranes or applying any heavy loads. So load restrictions is one of the challenges that we face. And by the time we get to actually identify and do the repair and so on, we are in well advanced state of corrosion where the reinforcement is completely lost or significantly corroded, where replacement of the reinforcement is required. And however, in order to do all this work, we still need to comply with our environment constraints, like encapsulating all the material and disposing it effectively. Then we do have heritage requirements that we need to comply. And one of the examples for the heritage is we have one of the oldest berth, which was built for defense. Right, I'm gonna just go back to this. Right in the corner here, that boom defense jetty, we call it. That structure has been very in a bad state. However, we cannot dismantle or dispose it because it's a heritage listed structure. So challenges, but and requires a long-term planning before we get to actually do some work. And from the inspections, we normally identify a section or via visual photos or some DLAM survey, but when we actually get to the site, the scope increases significantly. And we do face some challenges from scope creep, which again leads to the cost. And to do the works, remediation works, we do have various costs on top of the repair cost, like because there is shipping delays, we cannot just have one work platform, we need to have multiple. So the staging itself takes 7 to 10, and preliminaries all up, including planning, designing the remediation scope, and all the preliminaries constitute around 25% of the cost. Then the mob, demob, and contingency, and there is an escalation every year, as everybody is aware, with the cost prices. So overall, we are talking about for one berth. I can tell you some numbers from one of the berths that were inspected recently. It's around 2,800 square meters roughly of repair that is required, and we can estimate it's a significant amount of expense that needs to go in. But some of the incidences where once we get in, the defects are actually a lot worse than what we have anticipated. So we need to be prepared for that addition of scope to the cost to the remediation project. And access, in terms of height working for the people, we do have utilities that are operational, so we need to be mindful of that. And part of the project is we are trying to do is relocate some of the essential services from underneath the jetty or the berth, which were put in the previous construction phases, to the top of the berth, so that we are not interfering and disrupting those services in the future when we have to repair the concrete. And yeah, our problem as an asset owner is basically marine environment, different construction methods, different materials used during construction that are exposed to harsh environments. And by the time we detect the defects, it's too late. That is leading to high repair cost and downtime, and also some instances leading to safety hazards or risks. So we have certain areas on the port where we have barricaded certain areas because we have noticed the damage was a lot, and we cannot allow any people to go in that area or operate. So there are a lot of operational load restrictions in the port as we work through our remediation program. And to address this, we need to collaborate with industry experts, because it's a complex challenge driven by materials, environment, construction, and operational factors. And we need expertise from engineers, data scientists who can actually look at different data and then may provide more information on how, and put some logics and how the defects are progressing and what we are expecting out of the materials that are used in the concrete. And then obviously manufacturers of different products and some researchers. So we think that would close the gap of industry research collaboration, which would make innovations practical, social, scalable, and applicable in real world conditions, because it would be ideal for an asset owner to detect the defects early and preempt the amount of repair, the type of repair that we're gonna experience, so we can be more in a more proactive space rather than being in the reactive space. And yeah, that has a lot of benefits, because early detection prevents severe structural degradation and also reduces life cycle cost, minimizes downtime. And as you can see, being a very busy port with containers, liquid berths, and so on, getting an opportunity to perform these repairs is a significant challenge, because we cannot have much of a downtime on the berths. And doing the work safely and efficiently to keep the integrity of the structure for the port users is very essential. And by being in the proactive space, it also allows us to support sustainability by not introducing new concrete, whereas reducing the material waste, and we are not building or introducing new concrete assets. So that's something we thought is benefit for the asset owners. And I would now like to pass it on to Gavin for the next speaker.
Thank you, Rohith. Looking some very good photos there. If you're into concrete repairs, some very extensive breakouts, so I can see the benefit of this project. Our next speaker is Tasha Eagle. Tasha is the major projects and portfolio manager for Fosroc Australia and New Zealand, managing and supporting product and category plans to market. She is the technical lead for Edencrete, which is a new technology in concrete durability. Tasha's career in construction and the concrete industry has spanned 23 years, providing her extensive experience in concrete technology. She has previously worked for Boral, Hanson Construction Materials and GCP, and has held various roles in technical services, specifications, product and commercial sales management. Please welcome Tasha.
Thanks, Gavin. Thanks, Rohith. That was an awesome presentation. Let me bring mine up for all. And I'll just make sure you're not seeing presenter view. Full screen there, Gavin?
Yes, it's all
Perfect.
good.
Thanks for having me. Thanks for joining today, all. My story is more about the supply partner around being a part of these Smartcrete CRC projects, and this one specifically with Curtin University. Firstly, though, just a quick one. Who are we? Just so everyone's aware of who we are a Dulux Group company. And more than 12 years ago, Dulux Group bought a company called Parchem Construction Supplies. And Parchem Construction Supplies owns the exclusive manufacturer for global Fosroc products for Australia and New Zealand. So that's who we are in a very quick overview. What we do, Fosroc is a global company. As I said, it's been around for 80 years. Our products are a combination of in-house manufacturer as well as bought-in finished goods. What we do is pretty much anything to do with concrete. We can repair it, coat it, fix it, waterproof it, etc. And we do also have very good partnerships with some other companies that are associated with corrosion control. So Vector is a well-known company around anode and cathodic protection that Rohith even mentioned earlier. Edencrete is what I'll talk about a little bit today, but as Gavin alluded to, it's a carbon nanotube enhanced liquid additive for concrete durability, and we also do distribute Vandex products. So again, a broad overview. Today's not about a technical presentation from me to you, but very quickly, we've mentioned carbon nanotube technology, and that's why, and one of the reasons that we've played a significant part as a partner in this project. Carbon nanotubes in concrete are very new to concrete as an innovative material. Essentially, they make the concrete more durable because they're able to reduce the permeability of the concrete, and I'll show you some of the results we've achieved in this project today, and reduces the abrasion resistance and ingress of chlorides, etc., that, as we know, are corrosive to concrete. So yeah, durability, extending the design life of new assets, which can lead to sustainable options. And as Rohith mentioned before, some of our Fosroc products are there as sustainable options to repair rather than destroy and rebuild. So we are really about durability to market. What does it take to be a supply partner? Just a few key things here to share with you. It is a significant investment as a supply partner, supplying materials and support to Smartcrete and Curtin University over a 3-year period. As you can see there, $75,000 to be a part of this industry-led, very significantly required project, and that's why we wanted to be a part of it. What I have seen with new technologies in Australia, and again, Edencrete is one of them, Australia can be a little bit risk averse and slow to adopt. And so a lot of the feedback I've had, even though we do have some significant performance results here in Australia, it's about show us evidence. So as a supply partner, it's been really important for us to be a part of this project where we will actually see existing sort of performance results in the lab, but also out in the field, and certainly mixing it up with our asset owners, Rohith from Fremantle, and we have Southern Ports involved in this project as well. So that was important. And then time. Again, in the US, this technology is 10 years in, and it's about 5 years here in Australia where we have existing performance results. But as a supply partner of this project, it's going to give us more time. It's going to give us more time with the deployed samples that are out in the field at the port to monitor the results for a 1 to 5 year period. And so we have recognised that that is an important aspect for our industry and our asset owners in terms of looking at new technologies for durability. Again, if we look at the Smart Creek vision, it does talk about empowering research collaborations within our industry around innovative design, materials, technology to support concrete and sustainable Australia. So why would we be a supply partner? Again, we have an innovative material for concrete durability that I've just talked about. It does give you the opportunity as an engineer to potentially optimize designs for a sustainability aspect. It is a new technology, and it is operationally sound. So it's realistic. It's something that can easily be put into operations in a concrete plant and delivered into new concrete. And that's really important when we look at different materials and technologies here in Australia. There's a lot of things that are coming to light that we can use, but are they realistic in terms of the operational world? So I think that's an important aspect also. You can see some pictures here from the port. Our benefit as being a supply partner. Again, we're partnering with industry-led, recognised bodies, and obviously a very reputable university conducting trials and sharing results for industry. These data solutions, we hope, as a supply partner, that I will show you is, definitely adding performance benefits in reducing corrosion and chloride ingress, taking that to market, especially for our asset owners in marine environments, where, the asset owners and the engineers have the potential to adopt these durability solutions as a standard specification. And again, as a manufacturer and a supply partner, there's always going to be that commercial aspect for us in terms of we're here to support and add value, but we are a business and a manufacturer as well. So what are some of those results that I mentioned before? So some of the parameters in this particular project that we've seen, there's a bit of information up here, but essentially, and Kod may touch on this a little bit more, but there's been 30 prototype specimens, concrete specimens that have actually been put out in the port in the water, similar to that image you saw earlier. Those images were 40 years old and have been there for quite some time, but these ones have just been deployed this year. And the beauty is we're actually going to get to see the results and monitor these results, which is what Curtin University will be doing alongside Rohith in terms of what the durability aspects we're achieving with the control mixers versus the carbon nanotube technology in these 30 specimens over a 1 to 5 year period, which is really valuable for our industry, really, really valuable information. We've obviously had some specimens in the lab, and the key thing we've done with the specimens in the lab, and I'll show you these results coming up with these 10 different mix designs, is that we've conducted NORD 443 testing, so chloride ingress testing. So what Kod and the team at Curtin University have, and this is a snapshot for everyone, have been able to establish when they did these samples in the lab and tested them for the chloride diffusion coefficient, is you can see here with the different mix designs where we've played with 100% GP cement, a mix design where it's a combination of GP and fly ash, same with GP and silica fume, and then obviously the last one there being with slag. So what you can actually see is, different parameters, but we're seeing up to a 30% improvement or reduction in chloride ingress using the carbon nanotube technology when compared to just a standard 40 MPa mix design that's generally used out at the ports. And we did make sure that we were using, I guess, a mix design that's relevant to the industry and what the asset owners have generally used. And then again, looking at the reduction in penetration. So this is another test that the university have done, Kod and the team. And you can see here, we're seeing a reduction as well with the use of the carbon nanotube technology in terms of the penetration into the concrete. I'm just going to go back to this one. The one thing I forgot to mention is typically in the last 5 years here in Australia, with all of the other testing we've done, we have seen anywhere from a 33 to a 50% reduction in chloride diffusion coefficient results in various different mix designs. So we are seeing those results that we've found already being repeated in this collaboration, which is fantastic. So for me, the future, what does the future hold for us as a supply partner, industry-led supply partner in these projects? Again, we're here to try and help prevention of chloride and remediation with our products where we can help the asset owners. We're looking forward to the next 1 to 5 years of partnering and continuing to partner with Curtin University and Fremantle Ports around monitoring of our samples. As a supply partner, it's allowing us to have further industry collaboration and create those partnerships with the asset owners so that we can certainly support and help. We're bringing technologies for durability, to the market, not just with the carbon nanotube liquid additive, but also with our involvement with Vector and some brand new innovations in anodes, etc. as well. But ultimately, we'd really like to see industry adopt some of our durability solutions, especially the asset owners who we want to work with, and help extend the design life for sustainability for concrete, into the future here in Australia. And just one last thing, this is my last slide, Gavin, just wanted to add and let you know that we have committed significantly to Smartcrete projects, obviously this one that's ongoing to the end of the year, and then that continuation of monitoring in field. But we've also just signed up to a brand new project for the next 3 years, another Smartcrete CRC project around the development of sustainable and durable mortar, as you can see there, for ICC systems, and applications. And so that's a combination of using the carbon nanotube technology that we've talked about today, and one of our Fosrock Renderock G mortars. So that's just kicked off, and we look forward to those results too into the future. That's it.
Thank you, Tasha. Some very, very promising results there on the diffusion coefficient reduction. So looking forward to hearing how the project pans out. Our final speaker today is Professor Kod Pojtanabuntoeng. Professor Kod is the Woodside and Chevron Chair in Materials and Corrosion Engineering at Curtin University. She obtained her PhD in Chemical Engineering from the Institute for Corrosion and Multi-Phase Technology, Ohio University. Her research spans internal and external corrosion in oil and gas systems with expertise in carbon dioxide corrosion, top of the line corrosion under insulation. Since joining Curtin in 2012, she has led numerous industry-funded projects focused on solving practical corrosion challenges. She is an active member of the Australasian Corrosion Association and actively promotes collaboration between academia, industry to advance corrosion science and engineering education. Please welcome Kod.
Thank you, Gavin. Hi, everyone. Good morning, good afternoon, everyone. Following on from what Rohith and Tasha talked about, so we, in this presentation, we'll combine or bring together the bridge between the industry, the supplier, and what we do in the research laboratory, focusing on the complex phenomenon on the concrete corrosion in marine environment. So this project is a partnership between multiple parties under the Smartcrete CRC. We have Fremantle Ports as our industry lead, Curtin University, Curtin Corrosion Center, Civil and Mechanical, and a few other partner organizations, including Fosrock with Tasha as well. We work with Son and her team on the sensor, but in this presentation, we'll focus on just development of the prediction modeling and some of the experimental work to address the chloride diffusion. So I'll introduce the team. So the project is led by Sam and Farzaneh, who look after the Sam look after the modeling aspect, and Farzaneh look after the experimental aspect. But Today, Sam and Farzaneh could not attend today, so filling in the gap for today. We also work with a couple of data scientists from Trailblazer, which is another funding mechanism through Curtin and the Australia government to get the data scientists to assist in certain aspect of the project, which I'll cover that in a little bit. I think this slide is pretty much what we already understood in terms of the complexity of the aging infrastructure and what are the requirements for the new and sustainable infrastructure in terms of the asset integrity, how to ensure the service life and the longevity without prioritizing and minimizing the maintenance and so on. As we know that the concrete, as Rohith showed, multiple forms and multiple ways that the concrete structure can deteriorate. What the project focused on is a chloride-induced corrosion in the marine environment. And this slide basically shows a couple of mechanisms related to that. So chloride-induced diffuse into the concrete, destroying, compromising the passive layer and causing the steel reinforcement to corrode. The issue with that is the main question is how long will it actually take so that the asset owners can prioritize, can predict and scheduling those time to do the inspection before the failures occur beyond repair or costly repair need to be undertaken. So the project the main objective is to understand this diffusion to help with the initiation, to help understanding when the initiation would take place and when the action need to be undertaken. So mentioned before, the project has two aspects. The first one is the prediction modeling based on the data points that are obtained from the field, from the literature, from the experiments. From the data, we want to have a modeling that can understand the chloride diffusion from the trend from the field data. So in this case, we have Fremantle Ports as the source of our field data from the maintenance record that Fremantle Port has. Sam did the database or developed the database from the literature using not the experimental data, but more on the field data that are reported within the literature around the world, especially for the marine environment. The experiments as well. With a little bit caveat on the experiment is that there's always a question whether that experimental condition is how that can simulate the actual scenarios. So our model rely on the field data and the literature that based on the field data. Of course, we'll have the expert knowledge to help guide the algorithm to provide the weight and to confirm what the model predict is in line with the current knowledge or not. Now, when we develop the database, there will always be data that cannot be obtained, and there will be missing data, and there are practices in the data-driven modeling development is to impute the missing data. There are different categories, different technology that can be used to impute that missing data without causing a deviation from the reality. So there's that data processing, which takes quite a bit of work to understand, remove such an outlier, impute the missing data, and we correlate. We divided all the data that we have into two parts. The first one, 80% of the data is used as a training set. The remaining is used as testing. And we employ what we call a Bayesian network to develop that algorithm. And I'll show how that network look like in a little bit. And this map shows where our data come from Australia, Southeast Asia, some in the Middle East, and in Europe. So these are in the coastal and marine environment. This is our focus. 1,600 data divided into about 50 data points from the maintenance record from Fremantle, and the rest are from the literature again, but focusing on the field data. And this one shows how the Bayesian network currently look like. This is the network that we develop and using the chloride content as a output. So what we want to know is the tendency for the chloride content at a specific condition to reach certain value. So in this case, we have less than 0.1, 0.3, or more than 0.3. So this is the outcome of the model. And you can see the surrounding that outcome is the parameters that can be monitored and varied. For example, the environmental conditions. Here we could put a splash zone, submerged, or tidal zone. The age of that particular concrete component, being a different month or year, the chloride content in the environment. So here is in the seawater would be 35, 3.5%, or less than that. So yeah, for marine environment, it would be the 3.5. Water cement ratio at the moment, the mix, we have silica fume, slag, and fly ash. We don't have enough data to detail it for the percentage of each of these components yet. We only put yes or no. Yes, we have it, or no, we don't have it. And then the penetration depth. So this is how the relationship of each of the parameters and the chloride content at a given location would look like. This is an example. I'm sorry if it's too small, but this is an example of how we could use that model to give us the information, such as we can put, yes, the environmental condition is in tidal zone, 100% tidal zone. The age is a little bit older, more than 90 months. We look at the penetration depth of less than 10 mil. We don't have all of the mixture. We don't have any silica fume. We don't have any slag. We don't have any fly ash. In this case, 90% likelihood that we will have the chloride content in that particular location at the concrete depth of less than 10%, 10 mil, more than 0.3 weight% of concrete. So this is how we could use our the current established model. So the more data point we can incorporate into the model will be improved. Further on, with what Tasha suggested, that we had some samples deployed in the field that had carbon nanotube. We have a set in the lab as well. So in the future, we would, with enough data point, we will be able to have a box here to say, yes, how does the carbon nanotube impact and what's the prediction would look like in terms of the chloride content. So that's our update so far on the modeling side. Again, as with any data-driven technology, the more data point we could incorporate, the more accurate the data, the prediction would be. So to validate the model, what we develop is this come to the experimental part now. So to validate the model, we have to have something to verify that. So in this case, we develop the test protocol, which is a sample that enable us to not only look at the corrosion of the reinforced bar from the electrochemical side using the electrochemical impedance spectroscopy or electrochemical noise so this thing is a rebar. So there are 4 rebars. The dimension is given on the photos. So the idea for this is that we will go in interval and monitor the onset of corrosion through open circuit potential, passivity, or localized using the electrochemical noise or the impedance with the rebar. And once we notice that there are changes in terms of electrochemical activities, demonstrating either the passive film breakdown or active corrosion, then we can remove the test sample and can do the coring in the circle. The dash circle here are the area dedicated for if we want to do the coring afterwards to verify that activity from the physical and chemical perspective in terms of the chloride diffusion. The cross section of the this area can also be taken to look at the actual corrosion or the damage on the passive film on the reinforced bar. So this protocol or the test samples will enable us to support the model that we are developing. So these test protocol currently are deployed in the field, as Tasha mentioned. So there are 30 of them, 10 mixed design triplicates. And the idea is every few months we would go in and do the electrochemical measurement on this rebar to see the whether or not corrosion had been occurring yet. Of course, it's been only for a couple of months. We don't expect anything to occur to it. So probably take in a time period that was mentioned before. And these are deployed in the tidal zone. So this is on the low tide. I think when it's come to the high tide, it will come all the way to the top of the test sample here. A representative of each of the mixed design is also within the lab. And in this case, we do the accelerated test. So we do the cycling of the exposure to seawater. And also the cylindrical sample is same thing exposed to the seawater in the for the future to do the chloride testing. So the last slide is basically to show that to be able to address such a complex and a long period of phenomenon, what we employed is a combination of different ways. The lab study, field exposure. So this one is the old samples Tasha showed before, but the one that we presented is also just next to it. And previous reports. So we need to employ multiple aspects of the data that we can gather, and in this case, from 3 different locations, and to build the database to make the sense of all the trend of the data, to help the asset owner to predict, the diffusion of that chloride by ensuring that we have a robust data that can be fed into the system. We know that the prediction can be robust and reliable. Yeah, that's pretty much what I have.
Thank you very much, Kod.
Yep.
Looks like you guys have been very busy casting concrete and making samples. So looking forward to hearing how that research pans out over the next few months and years. Could I ask, Kod, could you remove your presentation? Yes. If we can get all 3 speakers to turn their cameras on, we'll open it up to questions. I think the best way to do this is if you use the raise your hand icon in Teams, and then I'll refer to you for the question. If you're too shy to do that, I'm happy for you to type something into the chat. So got a question in the chat from Karen Wilson. Welcome, Karen. With respect to the new test samples installed at Fremantle Ports, how will you avoid the risk of dislodgement of the block samples in extreme storm conditions?
I can answer that.
Yeah, I put the photo here, Rohith.
Yeah, we did notice that. So we did at the back end of the samples, there is a couple of like a timber that is drilled into the ground, so that acts like a barrier and not allow the samples to slip up. And we do have people monitoring in that area from time to time. But yeah, we did have enough barrier for the samples to be in place in the weather events. Hope that answers.
Yes. As you said, they look pretty heavy blocks as well there, but appreciate you can get, and I assume they're in the inner harbour as well, so behind a breakwater. But Yes, good. While we're waiting for some other questions, I've probably got a couple, maybe one for you, Rohith. I saw one of the photos you put up. There was quite extensive, as you say, surface breakout of the concrete associated with, assume, very bad deterioration. What are the sort of restrictions that you might put on for the extent of breakout? Because obviously there's a level of weakening, and you're trying to balance quicker turnaround times, etc. But just interested in your thought processes around any restrictions you had on work fronts and the like.
Yeah, we did reduce. I think that is one of the photos from the outer harbor berths. It was initially original design was 12-ton axle load capacity. So we reduced it to 10 tons and have a lot of other operational controls not to have any heavy loads while we do go through that deck for extensive period of time until we do the repairs. And even with the repairs itself, we have to do some structural modeling to analyze, okay, how bad we are and what we can allow and how much road restriction we need to put in before we can actually do that. So there were a lot of restrictions put in, basically. And there were some of them highlighted from the modeling itself. We have to come up with some of the critical areas that need to be addressed first and have a complete restriction on those beams. It's that particular structure is of a different. It's a complicated design as well. The way it is set up, it's not a simple structure. So we have to treat it very carefully and have the ship loaders and the trucks restricted accessing that on top of those beams, or long traveling on top of those beams.
Yeah, these things, as you say, complex in terms of concrete repairs, but also complex in terms of the operational restrictions. We've got a few more questions in the chat here. One from Sawn. This maybe one is directed at you, Kod. With the data set from varying regions in the world, did you separate and group them per region to study variations in the prediction output?
I can check, but I don't think so. Because the region would basically the submerged or the tidal zone only. Different region would probably affect the temperature and some salinity, but at the moment, I don't think we separate the region. We just the location in terms of submerged, tidal, splash zone.
Yeah. One for you, Rohith, from John Lee. What would be the early inspection detection period in years compared to the terrestrial inspection times?
I think, like I mentioned in a couple of photos, there were various, the age of the structure varies, and we do a periodic inspection of going to a full condition assessment of the berth every 3 to 5 years, but then we do accelerate or do frequent inspections in some of the areas. So it's hard to put a particular set time frame for across the whole of port, and we just prioritize depending upon, as we know, once we have more condition data, we know which ones we need to monitor more frequently and which ones we can delay and wait till the next inspection cycle. So
yeah, I picked up from your photos there, Rohith, that the 1972 berth 8, I think it was, you had quite severe corrosion with a photo in 1984. So it's only 12 years,
12 years,
and you've already got damage. And look, anecdotally, you would say 10 years structure you should have no problems at all, and you did. So I suppose trying to put broad blankets across times for early inspection, etc., is it's difficult given given a whole range of factors associated with mixed designs and quality of construction.
Thanks.
Yeah. maybe got one for you, Tasha. I look really impressed with the results you got for diffusion reductions in diffusion coefficient with the nanotubes. I was just wondering, as a liquid additive, are there any other factors you would need to consider in terms of, and I'm thinking more the plastic things like set time, workability, or strength gain, those sorts of factors? Does the carbon nanotubes have a positive or negative effect on those parameters?
Yeah, definitely positive. So from a plastic workability point of view, there's improvement. So we've seen improvement with concrete as placing it, pumping it, all of those sorts of things are improved. Definitely. Strengths, we didn't show a lot there. So we generally see like a 10 to 30% improvement in compressive strength as well in the concrete. And again, when I say that, I am generally talking, like a minimum 32 to 40 MPa mix design, which is generally where we're using this technology anyway. So all positives in terms of improvement, in terms of long-term strength. I do get asked a lot if it has HES, so high early strength. Not necessarily, but it certainly has no retardation properties either. So, yeah, it's all positive.
And in terms of, as you said, you're getting this quite substantial reduction in diffusion coefficient. How's that? What does it do to the concrete to get that reduction? Is it just reduction in pores, or subdividing of pores? How does it?
Yeah, essentially. So carbon, I didn't go into the technical spiel, but yeah, carbon nanotubes are nanoscopic, 1/50,000th the size of someone's hair, but they're really, really strong and flexible when compared to steel. And so basically what we see is, those little voids that would be there in a general mix are being filled with the carbon nanotube technology. Sitting in there, because we do hear about the plastic properties. It sits up better, it closes up better. So those strong little tubes are basically filling the voids, sitting in the top of the surface. They're giving you better abrasion resistance, and we're seeing that also with the chloride ingress results, but also the penetration results that the Curtin team showed. But I showed today as well. So definitely that. We do have an image showing a carbon nanotube having attachment to crystalline growth as well. So it was actually Deakin University in Australia captured that image 20 years ago, I think. So yeah, we do have evidence of that chemical function as well.
Very good. Any final questions before we wrap up? None at all. Maybe we've just got one more for Kod, then I will throw one out. So very interested in the modeling that you're doing, Kod, and the concrete technology and the diffusion characteristics. Just wondering, are you looking at the effect of those mixes on threshold level? Normally we sort of take an approximate level and say at this level everything starts corroding, but obviously the stability of that corrosion film is affected by a whole range of factors. Just wondering if you're looking at those components and feeding that into your model.
Yeah, that's the aim. So the experimental part where we have the test protocol, if we detect that the passive layer has been compromised, that would be resulting in the active corrosion, either reduction in the OCP, open circuit potential, or a higher corrosion rate determined from the other electrochemical techniques. Then we take out the do the coring of the test sample to determine the chloride diffusion, and then we can correlate. Okay, this chloride diffusion threshold that had been implemented in the past, does it really correlate with the initiation of the activity? So at the moment, we don't have that confirmation, but it's the idea of that test protocol that we designed for us to be able to address that gap. Yeah.
Very good. Very good. Okay, we're about on time there. As I said at the start, I'm very keen to keep us to schedule. So it just remains for me to thank our three speakers, Rohith, Tash and Kod. Hope you all found the talks inspiring. I certainly did. And look forward to seeing you all at the next community of practice meeting. Thanks, everybody.
Thank you very
Thanks,
much.
guys.
Thanks for the
Thanks, Ivan.
opportunity.
Thanks for
Bye.
having me.
Thank you.
See you. Bye-bye.